Well, we just got through learning about Euler's method to solve or approximate, estimate the solution to a differential equation, and it's considered a first order method. Only a first derivative was involved. Well, the next ones we're going to look at are called the Runge-Kutta methods. Runge and Kutta were German mathematicians doing their work around the turn of the last century. And they wanted to get a little bit more precise, more precision than the Euler method. But they didn't want to compute that second derivative to go to the second order term of the Taylor series. So Runge-Kutta, second order method, they needed more, this is accuracy, than Euler's method. So we recall the Taylor series, and we would get our next estimate of our y value from the previous y value plus the derivative of y with respect to x evaluated at xi, yi times the interval width. That's the first term. This is zero order term, the first order term, and then here's the second order term, 1 over 2 factorial. Second derivative of y with respect to x evaluated at xy times the interval width squared, and so on to get the third term, and then it goes on forever, the Taylor series. Another way of writing that, since we know dy dx will be given to us as f of xy. So we can simply say yi plus 1 is yi plus f of xi yi times h, the interval width. Remember, this is a derivative. This is dy dx. Plus 1 over 2 factorial times f prime of x1, xi, yi times h squared, plus and go on. Well, Euler used exactly these two terms. So what RK will use is these. Well, they'll look at these terms and then they will modify. So I'll say RK modify this expression right here so that this derivative does not have to be computed. Okay, let's say we have this differential equation. dy dx is e to the negative 2x minus 3y. So we call this function right here f of xy. That's our derivative. So f of xy is equal to this. And then the derivative is the partial of f with respect to x plus the partial of f with respect to y times dy dx. And that happens to be, I simplified it here, happens to be that. So using a second order method, we get yi plus 1 is yi plus, this is f of xy times h, plus 1 over 2 factorial times, this is really the second derivative, but it's f prime of xy times h squared. So we've got a second order formula. Well, RK, as I mentioned, wanted to avoid having to compute this symbolically. This is the second derivative. It's the derivative of this. So it's a second derivative, a second order term. So they came up with, so RK, I'm going to say implies, they came up with this formula. yi plus 1 is yi, just like before, plus a1 k1 plus a2 k2 times h. And then I'll define these terms, where k1 is simply f of x1, y1. Sorry, xi, yi. And k2 is a little longer, so I'm going to need to come back here. k2 is f of xi plus p K1H, comma, yi plus qii K1H. So we introduced some unknowns here that we'll discuss in just a few minutes. Specifically, we introduced A1, we introduced A2, P1, and QII. Now, QII, it probably is because in matrices, this happens to be an element along a diagonal. Just think of them as being 1, 2, 3, 4 different numbers. And they found that they were able to get basically second order accuracy, but notice there is no second derivative ever computed. What do we have here? We've got yi plus 1 equals yi plus, plus something. 2, we have a k1 here and a k2 here. And we're taking some linear combination of those two things. Well, notice what k1 is. That's exactly what we've seen before. It's just f of xi, yi. That's what was used in the first order Euler method. Plus a2 times k2. Essentially what we're doing, this is simply using f again, the first derivative, like this function. But what it's doing is saying, well, why, if we want to go from, let's say this is xi and this is xi plus 1, so this would be the height of yi. Why predict by just taking the slope here and predicting our next y value to be here? It's not extremely accurate. Why not move ahead some and compute another slope around, depending on what the parameters are, somewhere in between the two, maybe somewhere in here, and notice the slope here is closer to 0. Maybe average them in some way, weight them in some way, so we get something that looks more like this. And notice how much closer it is to the actual value at xi plus 1. So we're using this f of xy where we are, and then kind of in the direction of where we're going as well to get a better estimate of the slope. Okay, so what they did is they set this equation equal to the first 3 terms of the Taylor series, and they came up with this. Okay, they came up with this, and then I'm going to say comparing to first 3 terms of T series gave this for the 4 parameters. A1 plus A2 is equal to 1. So we're literally just weighting these two as 100% total, K1 and K2, but depending on which one you think you want to believe more, you might make it different than a 50-50, 0.5, 0.5. Could be 0.6, 0.4, or 0.3, 0.7. And then we got A2 times P1 equals 1/2, and A2 times QII is equal to 1/2. We'll notice that we have four unknowns and only 3 equations, so you can't solve for them. So what you or another person would have to do is just give one of them a value, and then based upon that, compute the other three. So that is kind of the basis of where we got a few different named methods that are based solely on the Runge-Kutta methods. And we'll begin the first one, Hoyne's method. I hope that's the way you pronounce it, Hoyne's method, in the next video.